Okay, so again, I just mentioned, I really recommend the question, what's going on here, every time you see something. Okay, focus on what's going on. Don't focus on how do I get the right answer, focus on what's going on, and that'll lead you to the right answer, hopefully. Or if you're in an engineering situation, you know, what's going on here? What are all the factors that affect this system? I'm supposed to troubleshoot, okay? And it's pretty natural to do that with engineering, but do it with problems you see. And so figure out what's going on, and then you are more likely to use the right concepts, techniques, formulas in your solution. Okay, so question, do you have particles? If you've got particles, then you're in the position of like X vectors and B vectors and A vectors and so on. And acceleration equals F net over M. P equals MV, 1/2 MV squared. You know how all those things connect, starting with the equations of uniformly accelerated motion, which you should be able to derive, and putting them together so you get the impulse momentum theorem and the work energy theorem. And then think about how to derive these things with integration. You should be thinking about that. It becomes more and more important as course goes on. Okay, so do you have particles? If so, here's your concept. If you have extended bodies, then you have theta, omega, and alpha. And I just commented that these things are vectors. Okay, at least a change in theta is a vector because you change theta from here to there. Your thumb's pointing in the direction of the change in theta vector, which is your omega vector. Okay, that's your angular velocity. It's got a direction. If you're rotating in this plane in this direction, then your angular momentum's in this direction. Angular acceleration, if the plane of rotation changes, then your omega changes. So you got a vector here, and now you got a vector here, and maybe this one's longer, maybe this one's shorter, maybe they're the same length, but whatever the change is from this vector to this vector, that would be a vector like so. And that's going to be in the direction of the average alpha. Takes the limit as delta t goes to 0, and you get the instantaneous direction of alpha. You want to understand all that because it helps you understand what you're seeing. Now, these came up because we were discussing the situation where the ball rolls down a ramp onto the tabletop, across the tabletop with negligible change in velocity, and hits another ball, goes off and hits two boundaries along the side. Okay, if we know enough information about those boundaries and about where the balls hit and when they hit, and we do because we did the experiment and we've got all the data and people gave pretty good answers to this last time, then we pretty much nailed that experiment. Now, in the sequence of questions that I asked about that experiment, the last question was, is angular momentum or any angular quantities relevant to this situation? And that's what we're discussing. So I'm going to stop talking for a minute. Let's see what we have to say about it. Too bad I can't name names because the person who told me this probably should become famous for it. But let's go into a little more detail. Okay, first place. I asked if angular quantities were relevant in this situation. First place, in the ideal situation where there's no friction, they wouldn't be. Okay, because there wouldn't be any rotation. If there's no friction, the ball slides down the ramp. It doesn't roll on the ramp. Okay, and it goes faster because more of the potential energy is changed to kinetic energy. Okay, so you might want to think about that. That's not real intuitive because you used to think spinning as they roll down a hill, which is a common experience. But if there's no friction on the hill, if you had a really, really icy hill and put that ball on it, it wouldn't spin as fast and it would tend to slide more than spin. There'd still be some friction, no matter how smooth the ice. Okay, well, in the situation that we observed, there certainly are angular quantities involved. Whether they're relevant to our analysis or not depends on things like, relative masses of the ball, relative sizes. In the comments, somebody said, well, yeah, because the ball spinning, if the second ball is much smaller, it's going to tend to stop it more. Okay, well, that's true. The reason that's true, the ball's spinning and hits another ball and there's friction, then there's going to be gearing. Okay, they're going to kind of lock for an instant while they're in contact, at least to some extent. They might slide, but and if there's no friction, then that's all they're going to do. They're going to slide. They're not going to lock. They're not going to change the spins, even if they have spins. Okay, but interestingly, the observation with the big ball and the little ball is that here's a big ball, here's a little ball. When they contact, they're not going to contact at the center of mass of this little ball or the horizontal center of the small ball. Okay, they're going to contact at some angle like this, which means there's going to be a good bit of normal force exerted by the big ball on the little one. The big ball is also spinning, so it's going to tend to spin the other ball the other way, and the other ball is going to try to lock into the tabletop, which is why that small ball will have more influence than the big ball. Now, if the big ball is moving fast enough, you also have the effect that you go into 3 dimensions. Okay, the ball could jump after it hit the second ball. So all that stuff has gone on. So that's a really good observation. At that point, you do have balls are extended bodies. They can't be treated just as particles unless you make assumptions. Now, we haven't included that in the analysis, but I could certainly ask questions about that. Give you the situation, give you the information, ask you to do conservation of momentum in 2 dimensions. Okay, that's easy. But then I could also ask you to speculate on the spin, especially give you some information, some quantitative information, maybe that allows you to do a little bit of analysis in that. Coefficient of friction is this, and they're spinning at this rate, and the contact lasts this long. What's the change in angular momentum? Yeah, it's worth thinking about. If I include something like that, it's only going to be for a point or so out of 10. Okay, I'm not going to risk your ability to pass the course and your whole future as an engineer on a hard question like that, but I might throw it in as part to separate out the A's from the B's, for example. Okay, and if I do that, I'm probably not going to do it with huge expectations. You want to see something reasonable, okay? Even if you don't get a rigorously valid answer to an off-the-wall question that we haven't really considered. I want to see if you can think through. I want to see what you think, and if you can identify the fact, okay, you have extended bodies and rotating, you're going to be in contact, which means they're going to have a frictional force. Okay, this ball exerts frictional force this way, this one exerts frictional force that way. Free body diagram, all that stuff. Okay, that makes sense. So you got to identify, first of all, you can't just treat these as particles, although at the first level, that's exactly what you do. You forget that they're rotating. We never talked about the fact that they're rotating, but now we do. They're extended bodies, and things can happen there because you don't have an isolated system. You have friction. Okay, you have friction with the tabletop, which wouldn't be relevant if it wasn't for the gearing plate and the other factors. It doesn't significantly change, but probably doesn't change at all, the results you get from conservation of momentum. Given the data, you'll still have equal and opposite momentum changes. Okay, well, I shouldn't say that, and I totally thought that through. Okay, well, anyhow, good observations. Okay, that's one situation. Basically, a ball strikes another one, and they fly off, and momentum is conserved in the X and the Y direction. Okay, now I've been talking as though what I'm seeing right here is simple harmonic motion. Okay. This end of the beam has an extra mass on it compared to this. So what's changed? What's happening to the potential energy of this system? Let me just change the orientation a little bit. Okay. What's happening to the potential energy? And what's the significance of that change? Because there is a change in potential energy. Okay, again, now I can get somebody else I can attribute a good insight to. Okay, so I asked, is potential energy changing? He said, well, yeah. And made a couple of statements, had me worried for a minute, because I guess the answer is because it's moving. And then before I was about to interject and say, well, it doesn't quite get it because potential energy doesn't necessarily change just because something's moving. And said, well, it's changing velocities, they're changing kinetic energy, and it's an isolated system, so there has to be a change in potential energy. Okay, that was a really good statement. All right, so love to see statements like that written on the fine. They make me happy. And if I'm happy, I don't think I'm really any more generous with grades. But if it's a good statement, I can take that into consideration. Okay. And maybe you get a point more than you would otherwise. Okay. So that's it. If the thing's moving and if it's changing velocity, which it certainly is doing, angular velocity in this case, as it's oscillating, there's no significant external force. I mean, there's a little air resistance, there's a little friction in the bearings, but those are relatively negligible. So you draw the conclusion. Now, is there another way to see that the potential energy is changing and actually to directly observe how much potential energy changes? Okay, so in discussion, it was said that trying to get, okay, I think we stated already on the video, but we know that the potential energy must be changing because the system's isolated, pretty much isolated, and the velocity is changing. How can we directly observe the potential energy? Haven't gotten a good answer to that yet, but we're getting there. What is it that causes a change in potential energy? Well, first answer I got was, well, potential energy, the beam is changing. That depends what you regard as the beam. If the beam is just the beam, the piece of shelf standard, okay, that's what it actually is. It's got very nearly uniform mass distribution, and it's rotating about its center, and its center isn't raising or falling, its center is fixed. So the beam is not changing potential energy. Okay. And then I said, well, what is? And the answer was, oh yeah, the magnet. Okay. And I said, yeah. And they said, what kind of potential energy is it that's changing? Is it gravitational, electromagnetic, Gremlin induced? And somebody kind of said, gravitational. Okay. When I heard the grav, I was afraid they were going to say gremlins. And that's actually probably in this lab, but let's just pretend that the only thing that's really changing, the only conservative force acting on that thing is gravity, okay? Gremlins, I don't know if they're conservative or not. Don't know how they vote. So we've established that somehow the gravitational potential energy of the magnet is changing. And somebody out there, well, how's it changing? And so, well, get closer or further from the center of the earth. Okay. Well, is the magnet getting closer or further from the center of the earth? Okay, so, the angle through which the thing is oscillating from stationary to stationary with equilibrium in the middle looks to be about that. What's that? It's not quite 45 degrees, I don't think. Let's pretend it's 37 degrees, because it's easy to find the sine and cosine. Although we don't really need it, but we might, okay? And it'd really be the angle between equilibrium and the extreme position that we'd want to think in terms of. So we're gonna say that angle's maybe around 20 degrees. It's going 20 degrees this side, 20 degrees this side, which is about a third of a radian. Okay? So a third of a radian from equilibrium. And the positions went from 21.3 centimeters to 21.0 centimeters, but I had the meter stick upside down. So that's what I measured. Now in lab, we write down what we observe. Okay. But the scale is actually kind of upside down. So we indicate that and try to make it clear. In our lab book, we're going to write down a statement, say, okay, had the stupid meter stick upside down, but it did change in position by a magnitude of 3 centimeters, 0.3 centimeters, and it got higher. Okay. Okay, at that point, what can you conclude? Okay, so, I said, what can we conclude? Then after I turned the thing off, I said, well, what can we calculate? And so I don't calculate the change in potential energy. You might have said the potential energy. If you said the potential energy relative to the equilibrium position, that would have been okay, but the potential energy depends on where you're measuring from. When you measure from the center of the earth, you're going to have a lot of decimal places in your answer. You're gonna have to use the law of universal gravitation. You can't use MGY. Okay. So you don't want to measure with respect to the center of the earth. You don't want to measure with respect to infinity either, because among other things, gravity is pretty much constant over a 0.3 of a centimeter distance. You could calculate that using the law of universal gravitation and resolve it. Anyhow, that's something I could well ask you to do. I'd have to state it a little more clearly than that. But okay, you got that distance and you got the mass of the domino, about 54 grams, okay? So it looks like you got 0.04 kilograms, which is 0.04 kilograms. To get that 0.054 kilograms, just say 0.05 kilograms roughly, through 0.003 meters, that's 0.5 newtons, 0.003 meters, 0.015 joules, okay? So it's a little high. 0.003 times 0.5. Yeah, there should be another zero in it. That's using 5 newtons instead of 0.5 newtons. Okay. So roughly 1.5 millijoules. All right. Well, does that match the kinetic energy of this system? How many radians per second at equilibrium? In other words, this should match the maximum kinetic energy of the system. So can you estimate how far would it go in a second at that speed you see right there? It's rotating about like this. So, okay, you can use your hand. It's rotating about like this. How long does it take to go through a radian, which is about this? 1,001, couple of seconds, okay? Just maybe moving at half a radian per second. That makes sense? Okay, well, we could compare its total energy at half a radian per second with this result. What do we need in order to do that? stop a second here and discuss it. Okay, bottom line, in order to start with what's going on here, we see that we've got particles, certainly there are particles. But we also have extended bodies, right? And the question is, what's its kinetic energy when it's moving at half a radian per second? Okay. Now, first of all, this half a radian per second corresponds to particles or extended bodies. Thumbs up for particles, thumbs down for extended bodies. Yeah, it's extended bodies, that's obvious. Everybody would get that. So how do you calculate the kinetic energy of an extended body? Well, an extended body can have just plain old 1/2 mv squared kinetic energy. If I take this piece of standard, which is just like the one that we have rotating, give or take a gram and give or take maybe a couple of microns of length, and throw it, okay, like this, and manage to throw it without rotation, it's certainly traveling through space and it has kinetic energy 1/2 mv squared. If I throw it like this, okay, take a big old throw and throw it 3 or 4 miles, okay? It's probably going to be rotating because of the way I'm using my wrist. And I'm probably going to get more speed on it than I would even if I didn't have the rotation. Especially, given the limitation of my shoulder, I can't exert this force through a whole lot of distance because the shoulder locks. If I do this, the shoulder doesn't lock. I get a lot more distance. I get torque exerted by my body, and this thing will go a lot further. Not nearly as far as it would have years ago, but you wouldn't want it to hit you. So it can have translational and rotational kinetic energy, both. Now, the system we're looking at, unless I'm walking around with the thing, is not going to have any translational energy. Right now, it's sitting on the tabletop. Okay. So it's all rotation. Now, somebody came up with it, how do you do that? Well, you do 1/2 I times that other thing squared. What's omega? Yeah, 1/2 I omega squared. And I did make the observation. It's good to know the words because they pop into your head. If you're having trouble getting, putting it together, which I don't think you would, but if 1/2 I omega squared is a sound that resonates with you, it's going to make it easier to think what you do. Okay, just have many ways to think about the same thing and to recognize the same thing. But you understood that you have to use a moment of inertia. Now, my question is, how are you going to get the moment of inertia? Okay, so I'll give you one hint. You could take a pair of really fine tweezers, take this thing apart atom by atom, and record how far the atom was each time from the center of mass, or from the center of axis of rotation, okay? And then add all those up. How many atoms are in that thing? Well, it's about 3 moles of steel, 2 times 10 to the 24th atoms, okay? So take you a while. And you'd have to calculate you'd have to calculate mr squared for each one. Does that make sense? Because how did we define moment of inertia? It's the sum of all your mr squareds. You really need to know that. Okay. Now we make approximations, but we can do an integration and figure out that the moment of inertia of that thing is 1/12 ml squared. Because it's uniform. It's close to being constant. The mass is close to being concentrated on a straight line. In other words, pretty close to a rod. And if you needed more precision, you can do the integrals if you need to, hopefully. Okay. And then we have magnet at the end. Okay. Roughly 50 grams at 30 centimeters. Okay. Most of the magnet is pretty close to 30 centimeters away. You'd use a parallel axis theorem if you wanted to get really close. You kind of want to maybe review that. Pretty important. just says that the moment of inertia of that magnet is the 1/2 mr squared you get when you go to the center of mass of the magnet, plus the mass of that rectangular, at the moment of inertia of that rectangular magnet about its center of mass. Okay? Because that magnet does have a moment of inertia about its center. You'd have to add that to the 1/2 mr squared. Okay? And that's because not all the particles are at 30 centimeters, and they're not all, well, the mr squared is not a linear relationship. And I'm not going to say too much more about that. But you get the idea that we could do the 1/2 ml squared. Okay. Mass is about 200 grams, is 1/12 ml squared. That length is about 0.6 meters. Square is 0.36 meters squared. And you multiply that by 0.2 kilograms, you get 0.072. Divide that by 12, you get 0.006 kilogram meter squared. You do that in your head, right? Well, I calculate that a couple of times a year, so I kind of remember it. I think it's probably right. So you got 0.006 kilogram meters squared. You got 30 centimeters, which of course squares to about 0.01, 0.1 meters squared. And you multiply that by the 0.05 kilograms. You get 0.005, so you get 0.011. Not sure about the right number of zeros there. Omega is about 1/2 radian per second squared. The square that's 1/4. Okay. So I omega squared is going to be about 0.003. And half of that is 0.0015, by darn. And that's just spooky. Because we're just talking ballpark estimates, but it came out exact. If I did that right. Okay. So you can check me on that. And I'd recommend you do that. It's, you know, we've talked about it. You got it pretty well in your head. You know what the system looks like. It gives you a lot of insight into this motion. Okay. Well, what else about this motion? Well, is it really simple harmonic? How would you determine whether the motion is simple harmonic? Well, the first response I got was pretty good. Said we could take data to get the position versus time, which we know to be like an A cosine of omega t plus phi. Okay. And from that equation and its derivative, which gives you the angular velocity, and the derivative of that, which gives you the angular acceleration, you put all that stuff together and see if it matches that model. See if it matches the circular model, basically. Okay. So that's a very good response. We could do this by interfacing this thing, because it does interface with our computer, and take pretty good data. I think you got a resolution of like 0.02 radians, something like that. It's not perfect, but it's pretty good. So yeah, we could see if it matches up. Okay. What else could we do to see if the motion is simple harmonic? Okay, well, we have one proposal is, well, it goes from here to here and stops and comes back to where it was and keeps doing that. We got an idea? Okay, we'll get it in a minute. And I just use the example of, suppose you got the Earth and somebody drops a big black hole here, it just passes through the Earth, goes to the other side, comes back, keeps doing that till it destroys the Earth. And it's a harmonic motion, at least approximately, keeps getting damped by running into the Earth, okay? But you get a differential equation out of that, you can't begin to solve, okay? And we can easily solve a differential equation. So what's a differential equation for simple harmonic motion? I think somebody's got it, we'll see. Okay, so I got something That probably related to something you learned in differential equation, which is pretty good stuff. Then you said something like mass double prime, well, it's mass times position double prime, okay? So it's like equals, no, you said, probably a negative CX prime, that would be a damping force, okay? And then said restoring force. Well, I hope you'll have that refined a little bit more, but that's a really good insight, okay? This would be a damped simple harmonic motion if you get the restoring force right. Pure simple harmonic motion, there's no damping. Okay. And I'm not gonna test you on damping. Jason, take care of that for you. Okay. You're getting a great differential equations course, but what's a restoring force? What do we mean by restoring force? What's the nature of the restoring force here? This is a linear. Restoring force. What's the form of a linear restoring force? Just let me know if you can tell me, and I'll pause. Not gonna wait long enough. Just because of time. Well, how many times have I written this? And I think at least one of you solved it when you didn't need to, but still got some points out of it on a test. Okay? It's a linear restoring force. It's a negative constant times your restoring force, times your position. And the position, of course, is measured from equilibrium. You need to know all that. Okay? Or instead of x, use theta, and you get exactly the same form of the equation. You have to use moment of inertia because we're in extended body, it's rotational and all that stuff, right? Make sense? Okay, so you solve these equations, you get x equals a cosine of omega t plus b sine of omega t, which is like a c times a cosine of omega t plus phi. Okay. And hopefully your differential equations got used to those manipulating those types of results, but that depends on how the course is being emphasized. But here, you know, they did be able to do those things. Still, what does this lead to? It leads to simple harmonic motion. It leads to everything that we've done here. And the spooky thing that happened, there must be gremlins around because I got the same answer here as I got here when there's no reason to expect that they'd be identical. I mean, they should be. But based on the uncertainty of the estimates that that were involved here, it's very bizarre that they are. Okay. Anyhow. Okay. Now the system where we have a magnet attached to the end of a car. I think we've got one sitting around somewhere that has a magnet on it, so I could demonstrate. But you know, there's a car. There's a big magnet. We put a little magnet on the end of the car and we pull it back here and release it and it gets pushed away. Okay. My finger did it there, not the magnet. The magnet does it. And I think we're pretty familiar with the fact that we have a force versus proximity graph. We've got a separation x, and the force falls off rather rapidly with distance. And other things that we were tested on at midterm, you know, you got a frictional force. So if you want the net force in this system, you got to subtract the frictional force from this. And eventually the net force is gonna go negative because the friction is going to exceed the magnetic force. And the friction acts in the direction opposite the magnetic force. Okay, make sure you try to remember that, because I am going to kind of emphasize these systems on the exam, simply because you have hands-on experience with the systems, you can visualize them, you know what they look like, you know how they behave. Okay. Anyhow, and people did pretty well with the problem I asked at the midterm. Okay. What's the potential energy function? How's potential energy related to force? This isn't. Magnetic force is conservative. Give you a minute to think about it, see if you can answer. Principle. The principle is equal and opposite to the work done by the conservative force relative to some reference position. What's a reference position? We're talking about gravitation. It's out there at infinite distance, or out there so far that any more distance doesn't make any difference. Okay, we've used that. So make sure you understand how it's been used and how it needs to be used. Here, what are you going to use for your reference position? Well, you know, I think an interesting reference position might be might not be able to read that. It says F net equals F mag minus F friction. And I'll even make a green curve. It's not very well made. My vertical distances aren't constant there, but I didn't want to take the time because we're kind of almost out of it. Okay, there's your net force, okay? If you've got a formula for this and know what your frictional force is, F net equals 0. Here, okay? Oh, you could do potential energy relative to that position, right? And you just have to integrate. It will involve we can call this the equilibrium position. Okay. Maybe it's a stable, maybe it's an unstable equilibrium position. It's not an equilibrium position for simple harmonic motion because you know darn well this system doesn't undergo simple harmonic motion, right? If you move it a little closer to the magnet, what happens? Well, that force is going to, okay, so that makes it an unstable equilibrium, doesn't it? Doesn't want to stay there. Now, if you move it a little further, because of friction, it'll still stay there, you know, but it would have to be stable in with respect to displacement both ways. So that's just something. Okay, Q involves an integral from equilibrium to position X of F of dummy variable with respect to the dummy variable. And that would be the magnetic force. Now, whether it's equal to that or equal and opposite to that, you can decide. Where's the potential energy going to be greater? Here or here? Okay. Does the conservative force do positive work on it or negative as you move from here to here? Does positive work, right? So it's equal and opposite to the work done by the conservative force. Okay, and that work is going to be greater here than here, so it's going to be greater in this direction. You have more potential energy the closer you put these things together, don't you? You can feel that. You have felt that if you've had your hands in the system, which I hope you have because we did it in the lab. Which is another incidental bit of advice to get your hands in everything that you do in the lab. If your hands are on it, it's going to make more sense to you if it comes up on an exam. Okay. So there we have it. So you do this integral and potential energy is greater here than it is here. So your U versus X is going to look a whole lot like this, but it's going to have a different shape. If this is an inverse cube, then you integrate an inverse cube, you get an inverse square, right? You have an inverse square potential energy for an inverse cube, make up potential energy, okay? Not the conservative force. Sorry. Okay, well, we're out of time. If you like, I can do a video where I rave on about the other situations on the handout. If you'd like me to do that, email me and ask me. Okay, you got to ask. Because if you don't ask, I figure you're not going to use it and I'm not going to do it. Even though I'd love to do it. Got a lot of other things that really need to be done too, so I got to prioritize. So give that a high priority by emailing me and I can tell you I'll do it. Okay. The test will involve situations that we've seen in lab, probably 50% of the test, okay? Probably 50% will be problems of nature that you've seen in the text and in the homework. Fair enough? Okay, well, listen, good luck. Y'all are very capable, so I hope it comes through in the final.